Okay. You can see my screen
Yes,
now.
yes, Sahar, you can start.
Okay. So my presentation tonight, my name is Sahar, and my presentation tonight will be about the concept of solar roadways. The outline would start with the definition, the conceptual design, layer details, the applications, solar energy potential and cost of adoption, the equivalent electric circuit, recent test projects, the barriers to adoption, and finally the conclusion and recommendations. So energy security is a sensitive topic in today's global economy, which makes sustainable development and reducing carbon emissions a priority. Researchers are trying to harvest electrical energy from the ambient environment by various techniques, one of which is the solar roadway technology. So what is a solar roadway? It is a technology that replaces all roadways, parking lots, sideways, driveways, bike trails, and outdoor recreation services with solar panels, but not any solar panels, with smart microprocessing, interlocking hexagonal solar units, transforming useless concrete roads that stretch everywhere doing nothing but reflecting sunlight and absorbing heat to units that actually produce energy. It has been estimated that if all roads in the USA were transformed to solar roads, the country would generate 3 times as much energy as it currently uses. And what makes this energy unique is that it is a clean energy. So what are solar roadways made of? Solar roadways consist of 3 layers as shown in the following figure. The road surface layer, which has the glass surface and underneath are the LEDs, and under it is the electronic layer, and finally the base layer. The road surface layer is the topmost layer, so it should be translucent and strong. It should provide great traction. It should be rough enough to provide great traction to prevent the skidding of vehicles, but at the same time, it should be translucent enough to pass the daylight to the reflector cells and the LEDs and the heating element that are embedded within it. This layer must handle the heaviest loads and be waterproof to withstand the worst of conditions while protecting the electronic layer that is underneath it. And tempered glass is the best candidate for this surface layer, given its smoothness and its solidity. The electronic layer consists of a microprocessor board with a supporting circuit for sensing the masses on the surface and at the same time controlling the heating element. Why the heating element? Because it will help in the process of snow or ice removal in the cold regions. This can also control any lighting system that is implemented on the pavements. And these microprocessor chips should be placed 12 feet apart, making the solar roadway an intelligent highway system that controls lighting, communications, and monitoring. The base plate layer, after the electronic layer collects the solar energy and transforms it to electric energy, the base plate layer distributes this collected power and data signals to all the networks connected to the solar roadway. This layer also has to be waterproof to protect the electronics from the underground water, and it is mainly made of recyclable material, and the main responsibility is to ensure the system has enough energy to operate itself before sending the rest of the power outward to the power grid. So the path of energy in the solar roads is that the sun rays are collected by the road surface layer, and then the electronic layer is responsible to convert this solar energy into electric energy, and the base plate layer is responsible of sending the energy outward or distributing the energy outward. So what makes solar energy, solar roadways so applicable? First, it leads to having an intelligent highway, saving global economies from the cost of maintaining the transportation infrastructure. So instead of using the government funds to build the asphalt roads, countries can invest in solar roadways, which will have high return on investments because it generates electricity, and it can have other forms of revenues as well, like they can be leased to service providers like communications or satellite or internet providers. So, and plus there will be no need for coal-fired or nuclear power plants. So the cost of these plants can also be reinvested in the solar roadway, because these can produce electricity up to 3 times more than a country's needs. So this infrastructure can be applied to enhance national defense security and mobility, defense mobility and security. How? Because they can use it to track the high-risk vehicles in real time. The second application is the illuminated roads. This technology promises implementing a LED lighting system which can reduce the accidents by 70% and at the same time save energy, especially in rural highways. They can light only when they sense moving traffic. Let's say before 0.5 miles ahead and 0.25 miles behind the moving vehicle. So this would increase the safety because the driver will know in advance that the car is coming from the other side. And also the LEDs can be programmed to light along the speed limit of the moving car. So the driver would know that he exceeded the limit. This can increase safety a lot. And they can also warn the drivers using the LEDs. They can flash words in front of them, controlled in real time as well. If any obstruction is ahead or any danger is ahead of them, or maybe an animal crossing the road, this also will increase the control and the safety. With global dependency on oil becoming more and more risky, solar roadways is offering a different option. Keeping up this pace, the world supply of gas has to increase to 120 million barrels a day in 2030. The US transportation system alone consumes 150 billion gallons per year. And the number of vehicles worldwide is expected to double by 2035. And since most of these vehicles are powered by fuel, this will definitely double the demand for oil as well. And what will happen when the oil runs out? And even if this still has like 50 years to happen, oil prices will increase when the reserves are becoming low. So Solar Roadways is offering this escape plan by replacing our highway with a system that will help us eliminate the need for oil at the end. A very important application as well is the electric vehicles. We all know that electric vehicles have been around for a while, but the main issue remains the recharging infrastructure needed to operate them in a practical way. The solar roadways present also a solution to this problem by allowing electric cars to recharge at any stop made of solar road panels. For example, drivers can recharge while shopping at a mall or eating at a restaurant. By providing recharging outlets practically everywhere, the electric vehicle would transform from a short-range means of transportation into a cross-country and high-range traveling vehicle that has no limits. The last application I'm going to tell you about is the power grid. Currently, the power grid that supply our homes and businesses are centralized power stations. They send power overhead or underground using transmission lines and transformers and relay stations. The problem with this power grid that we have now is that it's not stable because the outages are very probable to happen. So if we replace this centralized coal and nuclear powered station with solar roadways, we will have a secure energy power grid. How? This power grid, we can call it a smart grid, the solar roadway, is automated and is less prone to failures because we are decentralizing the production of electricity. Because every solar panel can produce a part of the electric energy and transmit it to the closed residential and industrial areas that are neighboring the solar panels. And these solar panels can communicate in a way that if one panel is down, it will be electrically isolated and the surrounding panels will take its supplied network, which would prevent power outages to a great extent. So solar roadways promise to provide a decentralized, safe, smart, and self-healing power grid. Let's talk about the solar energy potential. On average, sunlight on every square meter of land can produce 1799 kilowatt hour of power every year. And approximately 4,380 daylight hours per year is received everywhere on Earth. If you take a look at this figure right here, you can see that the global horizontal irradiance, the GHI, is, which is defined by the quantity of a given solar resource per surface area. We can see that it differs from one area to another on the planet. It's not constant. For example, in the Middle East, the average is between 1,800 and 2,300, while in Europe it drops to 1,200. What is important to note here that the developing countries, which are mainly at this area here, they receive solar radiation much more than developed countries, which gives these countries an advantage to develop their utility and move to clean resources in order to stop the consequences of climate change and increase their energy security. Talking about the cost of adoption, technological and technical improvements have decreased solar cell prices, and it has also increased their efficiency, which led to a 20% worldwide increase in solar cell installations in 2015. From this figure, we can note how the cost of solar PV has declined from 0.285 to $0.126 per kilowatt hour in 2015. At the same time, the cost of solar thermal energy also declined. This would attract the users to migrate to renewable energy resources because they would save their money and also be reducing the effect on the environment. Also, they would have greater control over their energy consumption if they are using renewable energy. However, it's important to note that in all my literature reviews, I found limited data on the cost of solar roadway installations, which is different from the concept of the solar panels that we use in the farms or on the buildings. For example, I found that the Solar Road test project, which was only 100 meters long, it costed $3.7 million, which is clearly much higher than conventional PV solar cell installations because the roadway requires special structural requirements. And of course, this small-scale project won't be very indicative of the terms of cost of a country of a country project, a big project. The model for the solar panel and the equivalent circuit are presented in the following figures. The inputs to the model are the voltage V and the solar irradiance G and the temperature T. The solar irradiance, which is the flux of radiant energy per unit area received by the solar cells, is given as an input current to a voltage-controlled current source. This input current is called the photocurrent, IL, which is equal to SCM, which is the short circuit current of a solar module, over 1,000 times the solar irradiance in watt per meter squared. The solar panel's equivalent electric circuit model, as shown here, is made up of a series resistor, RS, shunt resistor, RSH, and a diode. The series resistor represents the series resistive losses actually present in the solar panels, which is caused by the movement of current between the parts, and also due to the contact resistance. The shunt resistive losses, they occur because of manufacturing defects, and they tend to increase when the sunlight is minimum. The diode is used to protect the electric components from the current fluctuations. So the current voltage characteristic equation is given by this equation, where I is the input current, the output current, sorry, from the solar cell. The I0 is the dark saturation current, which is the diode leakage current density in the absence of sunlight. The V is the voltage at the output terminal. The RS is the series resistance. The RSH is the shunt resistance. The N is the ideal diode factor, which is typically between 0 and 1. The VT is the thermal voltage depending on the absolute temperature. And so we find the short circuit current by substituting V by 0 here. And the open circuit voltage is obtained by substituting I with 0. And these equations are for panels that have, because of course panels have multiple solar cells, they can be connected in series or in parallel. NS is when they are connected in series, and NP when they are connected in parallel. And here we assume that the shunt resistances are larger, so we can neglect their effects, and that the photogenerated current is equal to the short circuit current. So we can find the characteristics of multiple solar cells, the current and the voltage and the resistance. I'll talk about recent test projects. For example, in December 2016, France unveiled a 1 kilometer solar road made of photovoltaic panels. This was the longest solar road in the world. It costed $5.2 million. It was built using Collis Wattway technology. 2 years later, in 2018, it was already deteriorating. 90 meters were destroyed. The reasons were that it had cracks and that it had a lot of residues of leaves and dust on it. It was far less efficient than expected and too noisy to drive on. The tractors that drove on it increased the wear and tear, so they had to drop the speed limit to 70 kilometers per hour. In December 2020, also the United States unveiled its first solar roadway, which was constructed in Georgia. It was meant to produce more than 1,300 kilowatt hour of energy per year. It's mainly to recharge electric vehicles. Now, no information is available regarding its durability because it was very recent, but it is predicted that it's going to have the same fate because it was constructed using the same technology, which is the Collis Wattway technology. Okay, in the last part of this presentation, I'm going to address the barriers to solar roadway implementation and the limitations of this technology. The first limitation, which is the one of the major barriers to the widespread deployment, is the cost of installation. Despite the struggle of solar panel manufacturers to reach cost-competitive levels in comparison with other sources of electricity, and despite the recently reduced cost of installation of solar systems, the cost per unit of electricity produced by solar technology is still higher than that of conventional energies like fossil fuels and other renewable sources. It is estimated that it would cost $34.5 trillion to replace USA asphalt roads with solar roads, which is very high investment. And there is also the issue of maintenance cost of these roads, which is also very high. Another concern is the low efficiency and the low performance, which depends mostly on solar panels. Efficiency of PV systems is the lowest among all renewable and non-renewable technologies. For example, the single crystalline silicon solar cells, which have the highest efficiency, exceeds 25%. Another concern is the vulnerability to geographical locations and to the meteorological conditions, unlike the fossil fuel technologies that are constant. So many environmental factors affect them, such as the ambient temperature, the solar radiation, the humidity, the wind speed, and most fail to operate in cloudy and rainy weather conditions. And they are also very sensitive to manufacturing defaults. Another barrier is the low prices and abundance of crude oil and natural gas. Because global crude oil prices are continuing to drop, which makes the solar energy less attractive and less competitive when set against them. Moreover, the fossil fuels receive various forms of direct and indirect subsidy from governments, which hinders the investment in renewable energy technologies. We can notice on this graph that there's a huge difference between this, the fossil fuel and the renewable energy subsidies, and this is internationally. Also, another problem is the dust deposits, which is a site-specific problem and related to environmental factors like the soil material, the local microclimate, the intensity of the dust storms. This issue causes a significant reduction in efficiency, which can be up to 50%. Another problem is the shade effect. It also greatly reduces the efficiency. And there are two types of shades concerning the solar roadways. There is the partial shadowing that's caused by obstructions from trees and buildings. They are the main cause. And there is also the fast-moving shade that is resulting from the movement of vehicles on the road, or even sometimes from the traffic jams where the sunlight is blocked completely for a long period of time. So this needs great attention when designing the solar roadways. Also, there is the traffic load limits. The material selection for the top cover is very important because the normally used glass is not applicable. It's not strong enough to handle the load of vehicles. Many studies have been conducted. One was in Pennsylvania State University. They theorized a type of glass that has reduced flaws, which increase the strength. Another study in Missouri University of Science and Technology, they worked on the molecular level of the glass, or they used also special heating compressing techniques to make it 10 times stronger. More studies and experiments have to be conducted in order to come up with a reliable surface material that can handle the larger loads of traffic without breaking. The last barrier is the friction and the floods. To solve the problem of friction, there should be a granular surface layer applied. But this will reduce the rate of solar radiation a lot. Apart from friction, there is also the matter of flash floods, which happens when the water film accumulates on the top surface layer, which is very problematic. So the solar roads should be designed with elements that allow the rapid drainage of water, like the curb channels and the median drainages and the table drains. And further studies also need to be done in order to have a good hydraulic performance of the solar roadway. In conclusion, solar roadways, in theory, are supposed to create a smart and sustainable road infrastructure that pays for itself, to develop an intelligent, self-healing, automated, decentralized power grid, encourage the use of electric vehicles, increase road efficiency and safety, reduce our dependency on fossil fuels, and reduce the CO2 emissions by over 50%. But the problem is they have more limitations than applications, as we saw together. So the recommendations would be that governments have to frame a chain of policies on solar energy development, to limit the reliance of fossil fuels and biomass resource, and maybe instead of providing the subsidies on fuel, start to provide the subsidies on renewable energies like solar energies. And manufacturers, on the other hand, have to meet the governments halfway by focusing the R&D to offer new material and applications that could serve the technology, and provide also encouraging prices that would encourage the users to switch to solar roadway technologies. In conclusion to everything in this presentation, the solar roadways unfortunately won't be a reality until a long time in the future. Thank you.
Sorry, Sahar, علقت الماوس شوي. Okay, thank you so much.
Okay.
It's a nice work.
Thank
Just as your conclusion said, so until now, the expectation were not met concerning solar roadways. But are we trying to go more over research to see how we can have it realizable as a project? So when you did a literature review, do you have, are you seeing that this research is under development, or we decided that it's not effective?
What I found is that the inventor he and his wife, they were the ones who came up with this project. They are still working on it. And the countries are still trying to make to implement small scale projects. The last one was in 2020 in December, so it wasn't long ago. They didn't lose hope on it. They are still trying to improve, and they are still trying to come up with the material that would work for it. But it still needs a lot of time to become a reality.
Did you find something about economical studies as the one we did together today? So if they are performing a certain life cycle cost, to see what can be the strategies to do to make it viable economically?
The main issue is the price of the installation. The cost of installation is really high. That's the main issue. So if the manufacturers can find a way to reduce this cost, it would be economically viable. But now it is not. It is not at all. In developing countries, it would need funding from institutions, from financial institutions and from international donors, so that they can be able to implement such projects. It won't be easy.
Yeah, I see. Okay, thank you, Sahar.
You're welcome. Thank you.
Okay, bye-bye.